Hello everybody. Today I'm going to be making a video on transfer functions and why they're important in this class and why they're important in when you're using control systems as an engineer. So what is a transfer function? A transfer function is just something that can represent the ratio of what an output signal is to the input signal, typically in the frequency domain. And the importance of this is instead of using big complex differential equations that involve a lot of calculus, we can use transfer functions instead to use simple algebraic steps and equations. Um, like I said, there's many domains that transfer functions can be seen as, and depending on which domain you want to see a transfer function to be in, is going to depend on the transform that you use. And right here, I have three transforms that you can use, which are Laplace, Fourier, and then Z transforms. Typically, when you have time involved in one of the equations, it's typically going to be the time domain over the frequency domain, and that's when you would use Laplace transforms. Fourier transforms you typically use in a JW plane, and Z transforms you would use when you're trying to find something over discrete time, and that's something you'll learn later in the semester. I'm not going to sit here and try to go over that. I'm just going to explain to you guys how you derive transfer functions in RLC circuits. So right here we have an RLC circuit. We have a capacitor, resistor, and an inductor. We have a resistor and an inductor in parallel with each other, which is all in series with a capacitor. So the values we have here, I will show you guys the steps and how to solve this. So first, we have to see what is it that we're even solving for. So like I said, a transfer function is always seen as V out over Vn. And how do you get that? So what is V out over Vn? So what it is it's the impedance that's in parallel with each other over the input impedance. So what we need to find first is what the input impedance is, because when we do that, we'll be able to also get the parallel impedance as well. So let's start off by looking at what we have. So like I said, we have a capacitor, we have a resistor, and we have an inductor. So first, what you want to do is obviously find Zn, and with these values that we have over here, we're going to be able to make a transfer function from that. So, like I said, since that capacitor's in series with the what is in parallel, we'd first want to start off with 1 over 2s, because, like I said, this is what we're trying to find in the frequency domain, so we're going to be using the s domain. So, we're going to use what we have in series and what we have in parallel. So, it should look like this. So, we have a component of 5 ohms times the 3s, which is the inductor, over 5 plus 3s, because those are what are in parallel. So as we can see here, we just found right there what the parallel impedance actually is. So what I like to do is just make a little box and draw an arrow off and just kind of let myself know that's what the parallel impedance is. So basically all we do from here is, like I said, just algebraic steps. So we're basically just gonna simplify this a little bit more. So it would be 2s, 5 plus 3s, plus 15s times 2s over 2s times 5 plus 3s. And that's what we got so far. I'm just going to drag this down here. And when we simplify this, we are going to get 30s squared plus 3s plus 5 over 2s times 3s plus 5. I'll put that in right there. And then what we can do is we can distribute this. So on top we can distribute a 5 out. So that would be 5 times s squared plus 0.1s plus 0.1667 over S times S plus 1.667. And down here, all we did was just distribute an S up. All right, now that we have that, this is what our Zn would be. So we found what we needed to get V out over Vn, but we have not solved for that yet. So I'm just going to turn the page over here. All right, now that we have that, now we can actually solve for the transfer function. So we have V out over Vn, which is equal to our parallel impedance over our input impedance. So what did we find with what we boxed first with the parallel impedance? We found that to be Cp 5 times 3s over 5 plus 3s. So that's what we found there. And then Zn would just be the whole transfer function that we found on the other page. So we just put Cp over Zn. So it should look like this. And I'm just going to make this look a little bit different. But all this is just, excuse me, 0.5s parallel over s. So the only difference that we have here is just the top. I just multiplied the 5 back in, just so it's a little bit easier. And then make this look a little bit neater. Now, again, it's just algebraic steps, just a little simplifying. So this part would be a lot easier just to plug into our calculator. So if you have a TI Inspire, make sure you use it. Most important thing. S plus 0.8333. All right. So what we have basically here is, all we did here was we just put the parallel impedance over the input impedance, and right here just made it look a little bit neater and easier to work with for us to put it in our calculator. The thing with a calculator and doing it handwritten is you always want to do both of them, just because you always have a check. If you do it with your hand, then you have the calculator by check, and if you just go ahead and plug it into your calculator all at once, you should still do it by hand after, just so you have that check and just so you can make sure you can compare. But I'm just going to contradict myself here and throw it all in my calculator, and you should get an n number of s squared over s squared plus 0.1s plus 0.1667. And what we have here is we have V out over V in.